Welcome to G Fun Facts Online. Imagine a library, but instead of books, the shelves hold cylinders of ice. Each one is a frozen chronicle, a detailed history of Earth's climate going back hundreds of thousands, even millions of years. These are ice cores, and today we're diving deep into the science of how these frozen archives reveal our planet's astonishing past. Deep within the vast ice sheets of Antarctica and Greenland, every year, new snow falls on top of the old. This snow never melts. Instead, it gets buried, compressed by the weight of subsequent layers. Imagine piling thousands of blankets on top of each other. The ones at the bottom get squashed flat. The same thing happens with snow. First, the fluffy snowflakes get squeezed into a dense, granular material called firn. As the pressure continues to build, sometimes under hundreds of meters of more snow and ice, the firn compacts even further. The tiny air spaces between the grains get sealed off, trapping little bubbles of the atmosphere from that exact moment in time. Eventually, the firn transforms into solid glacial ice, and those bubbles become tiny time capsules. This layering is the key. Like tree rings, each layer represents a specific period, with the newest ice at the surface and the oldest at the very bottom. This simple, elegant process creates a continuous timeline of Earth's climate history. But how do we get to it? Retrieving these frozen memories is a monumental feat of engineering and endurance. Scientists and engineers set up camps in some of the most hostile environments on Earth, battling sub-zero temperatures to drill deep into the ice. For shallow cores, a simple hand auger might do the trick. But to reach ice that's kilometers deep, they need sophisticated machinery. The most common are electromechanical drills. These are hollow barrels with a rotating cutting head, suspended by a massive armored cable that also provides power. As the drill carves its way down, a perfect cylinder of ice enters the barrel, which is then hoisted back to the surface, section by section. Once a core is extracted, it's handled with extreme care. It's meticulously cataloged, stored in frozen containers, and shipped to specialized labs around the world. In these ultra-cold, clean facilities, the real detective work begins. Before you can read the story, you need to know the timeline. So how do scientists date the ice? For younger ice, often going back tens of thousands of years, scientists can simply count the annual layers. Just like tree rings, seasonal changes in snow accumulation and chemistry create visible bands. You can literally count the years. But deeper down, the layers become so compressed, they are impossible to distinguish visually. Here, scientists look for reference horizons. Think of these as bookmarks in time. A massive volcanic eruption, for instance, spews ash and sulfates into the atmosphere, which then settle on the ice sheets. If we know the date of that eruption from historical records, finding its ash layer in the ice core gives us a precise time marker. For the most ancient ice, they turn to radiometric dating. Just like carbon-14 is used to date organic remains, scientists can use isotopes like krypton-81 trapped in the air bubbles. Since we know the exact decay rate of these isotopes, measuring their amounts tells us the age of the air, and thus the age of the surrounding ice, potentially pushing the record back over 1 million years. With the timeline established, scientists can start analyzing the climate proxies. These are the preserved clues that stand in for direct measurements of past conditions. One of the most powerful proxies is the ice itself. Water, or H2O, is made of hydrogen and oxygen. But not all oxygen atoms are the same. There are lighter isotopes, like oxygen-16, and heavier ones, like OXyGen-18. As water evaporates from the ocean and travels toward the poles, the water molecules with heavier isotopes tend to rain out first because they're heavier. This means that the colder the climate is, the less heavy oxygen makes it all the way to the poles to fall as snow. So by measuring the ratio of heavy to light oxygen isotopes in each layer of the ice, scientists can create a continuous, detailed record of past local temperatures. It's like having a thermometer that reaches back through the ages. Then there are those tiny trapped air bubbles. These are arguably the most extraordinary feature of ice cores. They are not just clues. They are actual physical samples of Earth's past atmosphere. Scientists can carefully extract the air from these bubbles and directly measure the concentrations of greenhouse gases like carbon dioxide and methane from thousands of years ago. And what this has shown is nothing short of revolutionary. It's this data that first provided the ironclad link between atmospheric CO2 and global temperature. Beyond water and air, the ice traps all sorts of other interesting materials. Dust, for example, tells us about past wind patterns and aridity. More dust usually means a colder, drier, and windier world. Volcanic ash, as we mentioned, helps with dating, but also records past volcanic activity, which can have its own cooling effect on the climate. Even chemicals like sea salt get trapped, giving clues about the extent of sea ice in the past. Shockingly, these cores also preserve a record of human activity. Lead pollution from Roman-era mining and smelting has been found in Greenland ice, as have radioactive particles from 20th century nuclear bomb tests. The ice forgets nothing. So, what are some of the biggest stories the ice has told us? In Antarctica, the Russian Vostok station drilled a core that went back over 400,000 years, covering 4 complete ice ages. The data showed a stunningly perfect dance between temperature and the levels of carbon dioxide and methane. When CO2 was low, the world was in an ice age. When it was high, the planet was warm. Later, the European Project for Ice Coring in Antarctica, or EPICA, drilled an even deeper core at a site called Dome C, extending this record back an astonishing 800,000 years. This incredible record confirmed the tight link between CO2 and temperature. It also established the natural range of atmospheric CO2. For 800,000 years, CO2 levels naturally fluctuated between about 180 parts per million during the coldest ice ages and about 300 parts per million during the warmest interglacial periods. Today, atmospheric CO2 is over 420 parts per million and rising fast. The ice cores prove, unequivocally, that we are in completely uncharted territory. While Antarctica shows this long, stable rhythm, ice cores from Greenland tell a different, more violent story. The Greenland ice sheet revealed that climate change can be incredibly abrupt. One of the most famous examples is the Younger Dryas event, around 800 years ago. The Earth was naturally warming out of the last ice age when, suddenly, temperatures in the northern hemisphere plunged back into near-glacial conditions. This cold snap lasted for over 1,000 years before the climate just as suddenly warmed again with shocking speed. We're talking about temperature shifts of more than 10 degrees Celsius happening in just a few decades. The Greenland cores show that the climate system doesn't always change gradually. It has tipping points and can reorganize itself with breathtaking speed. Of course, ice core science isn't perfect. The records are mostly from the polar regions, and the details can get fuzzy in the very oldest ice. That's why scientists work to combine ice core data with other climate archives, like tree rings, cave formations, and ocean sediments, to build a more complete, global picture. Today, the quest continues. The Beyond Epica project is on a mission to find the oldest ice, hoping to drill a continuous record back 1.5 million years. This could solve a major climate mystery: why Earth's ice age cycles suddenly changed their frequency around 1 million years ago. But there's a new urgency to this work. Many of the world's high mountain glaciers, which hold unique climate records, are melting at an alarming rate. Projects like the Ice Memory Foundation are now in a race against time, drilling cores from these threatened glaciers and storing them in a secure ice archive in Antarctica. They are creating a library for future generations, preserving these irreplaceable records before they melt away forever. From a simple snowflake to a kilometer-long cylinder of ice, these frozen chronicles have completely rewritten our understanding of the planet. They have shown us the powerful link between greenhouse gases and climate, and revealed the Earth's capacity for sudden, dramatic change. As we face our own climate challenges, the stories locked in ancient ice provide a vital perspective, a stark warning, and an invaluable guide for the future we are all shaping.